When we consider the soils of the Buckleboo district and the Eyre Peninsula more generally, we find that we can broadly classify them into a few main types, such as high pH calcareous loams and shallow soils on rock, red-brown earths, deep sands and sand over clays, and ironstone soils on lower Eyre Peninsula, which can be acidic. The reason for different soil types comes down to the soil formation processes, including the parent material, such as limestone or granite, whether the soil was formed in place or moved in from elsewhere, and the impacts of climate and organisms over time. The types of native vegetation present can indicate soil type and implications for crop production. For instance, low saltbush shrubland tends to dominate the shallow calcareous and hard setting soils in the lower rainfall environments. Sandier dunes, which are the result of later deposition of wind-blown sand particles across much of central Eyre Peninsula, grow open mallee scrub with broom bush understory. Each of these soil types has its own implication for production and management. For example, around 85% of the area cleared for agriculture on Eyre Peninsula is considered to have low to moderate inherent fertility. Much of this is because it has high amounts of free lime, which reduce nutrient availability, or it has sandy texture, which limits the capacity to store nutrients. In addition, about 15% of the area cleared for agriculture has moderate to severe water repellents at the surface, which restricts plant germination and growth. And also around 8% of the agricultural area has soils with poor structure, causing hard setting layers. So one way we can better understand the role of different soil types in crop production is to dig some holes and have a look at the different layers that are present there. The different soil layers are referred to as soil horizons. The top layer, which is largely a mixture of mineral soil and organic matter, is referred to as the A horizon. The deeper layers, which are just mineral soil, are referred to as the B horizon, with the C horizon kicking in once we get sort of into the weathered basement rock. So the different soil layers can tell us a lot about the productive capacity and different management issues. For instance, this darker layer here is an indicator that has higher organic matter, which has higher inherent fertility than this lighter layer deeper down. So we can see a bit of compaction in the next layer down, which would restrict root growth and crop production as a result of that. So, and then once we get down into these white nodules, we're looking at high amounts of free lime there, which can limit the availability of different nutrients. So it's easy to test for free lime. We can do a simple test using some acid, dropping some acid on it, and just looking for a fizz reaction. So just a couple of drops of a dilute acid solution gives us a high level of fizz, indicating that there's high amounts of free lime with the potential to significantly tie up some of the nutrients there. The different soil characteristics which impact on production can be broken into two main types: soil physical and soil chemical properties. The key soil physical properties are soil texture and soil structure. Soil texture is the relative proportion of sand, silt and clay in the soil, which impacts on water and nutrient holding capacity, as well as indirectly affecting water repellence and erosion risk. So to assess soil texture, it's a relatively simple field test. So we just basically take a small handful of soil, add a little bit of water, form that into a bit of a soil ball. So we want to make sure that it's evenly wet and that you've sort of broken down all of the soil clumps. And then once you've got a nice even ball, you want to sort of work the soil out between your thumb and forefinger to form a bit of a ribbon. And the length of the ribbon determines what the soil texture is. So that one's about 2.5 centimetres, so you're looking at a loamy soil texture there. And also loamy, like it's a little bit spongy, so that indicates that it's a loam as well. Sandy soils are inherently more prone to erosion because the particles do not easily bind together to form aggregates like clay particles do, and as such are more easily picked up and transported by the wind. Because sand particles have a much smaller surface area than clays, oils from the breakdown of organic matter can coat the sand particles, forming a water repellent layer. The addition of clay to the soil by clay spreading or delving increases the surface area, diluting the impact from the waxy molecules and helping the soil to wet up. Because sands have a coarser particle size than clays, there is less space between the particles, and as a result they can't store as much moisture as clay soils. They also can't attract and retain as many nutrients. Soil structure refers to the way that soil particles are arranged together and impacts things like surface sealing, compaction and drainage. Poor soil structure can be the result of either physical disturbance or chemical imbalances. It's often observed as a layer of high soil strength which restricts root growth and can be measured using a soil penetrometer. If compaction forms as a result of mechanical disturbance or machinery traffic, soil modification practices such as delving, deep ripping or spading can help overcome this. If the poor soil structure is a result of chemical imbalances, such as a high amount of exchangeable sodium, then amendments such as gypsum might be needed to address it. Soil chemical properties can be tested by sending a sample to the laboratory for analysis. Soil pH measures the acidity or alkalinity of the soil. At the extremes of these pH ranges, plant growth can be impacted because nutrients are less available, soil microbial activity is inhibited, leading to poor crop, water and fertiliser use efficiency, and in some cases, particularly under acidic conditions, toxic elements such as aluminium might be more available. The inherent fertility of a soil is the capacity for different types of soils to hold on to nutrients. Clays generally have a negative electrical charge and have many sites where positively charged nutrients such as magnesium, potassium and calcium combine to the soil particles. This is called cation exchange capacity. But sands generally have a neutral charge and so can't bind to these nutrients. Organic matter has a very high capacity to attract and hold nutrients, and the cation exchange capacity of a sandy soil can be improved by adding clay or organic matter to it. Other chemical parameters which impact on crop and pasture growth are toxicities such as salt or boron. Analysis of the soil electrical conductivity can provide an indicator of the potential salinity impact on crop growth. So how can we use this knowledge of soils to better manage both the productivity and sustainability of the soil resource? Firstly, by understanding the soil physical and chemical parameters, we can identify potential issues for agricultural production, helping to guide management decisions. We know that sandy soils are more prone to wind erosion than clays, so it is important to reduce the erosion risk on these soils by minimising soil disturbance and retaining as much surface cover as possible. We also know that most crops and pastures are more productive when pH is neutral, so it's important to address soil acidity by liming. Whilst there's no cost-effective methods for reducing the pH of highly alkaline soils, it's important to try and address nutrient limitations by supplying adequate amounts of nutrition in an appropriate form and by implementing management practices which improve soil microbial function. By understanding our soils, their limitations, and then applying appropriate management strategies, we can maximise the productivity and improve the sustainability of farming them.